Hi everyone, welcome. This is the first video for Gen Chem 2. We're going over chapter 6, thermochemistry. Here's all your homework assignments. These are all on mastering chemistry and they're the same problems. Some people like to work with pen and paper better. So these, if you're using the book, these are the numbers you want to do. Here's week 1 from chapter 6. There's the page number that you can start on. These are for week 2, and there's also some from chapter 9, so just make sure that you do that number too. And then week 3 is actually from chapter 11, that's your thermodynamics chapter. And again, these are all on mastering, so I don't care how you do them, I just want you to do them. So basically what we're first going to talk about is energy that is heat and how it is transferred from one thing to another. So thermochemistry deals with different materials that are maybe at different temperatures, or even the same material that has a temperature gradient, so some is hotter than others, or a chemical reaction that will either require heat or expel heat when it occurs. And we basically just are studying how that happens, where the heat comes from, doing some calculations with that. So that's what we're talking about. We're talking about thermal energy. So if you have like a container, right, and there's a partition in the center, and one side you have sand, let's say the sand is energy. So this has a ton of sand in it, so this is your hot side, lots of energy. And over here, there's only a little bit of sand, so that's cold. That's your cold side because there's not so much energy. If you go in and you remove your partition, and you take this out, what's going to happen is this sand is going to sort of level out and all of it's going to pour into the other side. So at the end of your experiment here, you're just going to have a big beaker of sand, and all that sand is going to be at the same level. That is thermal equilibrium. All right, so that's where you have something that was hot and all that energy poured into where there was no energy, which is your cold part. So heat always is going to flow from hot to cold. So if something makes you cold, it's taking your energy, it's taking your heat and using it so that you feel cold because it's stealing it from you. So that's how heat is transferring from one thing to another. All right. So our objectives with this chapter is to talk about internal energy and its components, heat and work. We're going to define the first law of thermodynamics. We want to differentiate between heat and work and also differentiate between energy and enthalpy. So the first part is all about internal energy. And then we're going to introduce enthalpy, which is delta H, and we're going to talk about why they're different. We're going to do some calorimetry problems. This is what both of our labs for this section will be on calorimetry. And then we're going to talk about enthalpy and calculate and measure the heat of a reaction using delta H. So that's what this chapter is about. All right. So first we're going to just talk about the energy that is stored somewhere and energy that's going to be used to do something. So energy is just the capacity to do work. So if you want to move a table across a room and you're going to push it, that's the work you're going to do. The work that you put into it is your force acting over a distance. Okay, so that's you pushing over a distance. Your muscles, your body is going to burn ATP, and you are going to, heat up in order for that to happen. So there's always a heat component when work is done. So we're going to just talk about how work and heat go together to determine your total energy of a system. So that's what we're going to talk about. All right. Here's a little diagram that I got from a different book that just sort of breaks down the two different types of energy that we're going to talk about. So kinetic energy is just motion. What temperature is a measure of the kinetic energy of a sample. So if it's hot outside and we measure the temperature, and let's say it's 80 degrees Fahrenheit, what that means is that your air particles are moving around at a certain velocity with a certain amount of energy. So they're moving really fast. When it's cold out, they slow down. We're just measuring the motion of those air particles. Potential energy is sort of the energy that is like innately stored somewhere. So it could be due to the position of that object, or its composition. And so when we talk about chemical energy, we're talking about the energy that is associated with its bonding properties. So positions of electrons, where they're attracted to the nuclei and how they're interacting together. So that's our chemical energy. We're going to mainly focus on thermal energy, but both components are important. All right, first law of thermo, conservation of energy. The total energy of the universe is constant. We cannot destroy energy, but we can't create it either. It just transfers from one to another. I assigned a video in mastering that talks about this, so I'm going to just let you watch that, and I'm not going to go into it any further, but you need to know that this is the first law of thermo, it's just the conservation of energy. We are going to define what your system is and what the surroundings are, because that is where your heat exchange is going to happen in a lot of our calorimetry and other problems that we're going to talk about. So here's your system. Your system is basically whatever the reaction is. All right? So that's the system. If your reaction gives off heat to the surroundings, which is the beaker, the water, the bench that it's on, the air that surrounds it, anything, if heat is released, it's called an exothermic reaction. Okay? That heat is leaving the system and it's going into the surroundings, so that's exothermic. So a fire, for example, burning of wood, carbon, that's an exothermic process. We can feel the heat coming off of it. Say opposite situation here is when you have your system, your reaction. If that requires heat, it's going to steal heat from wherever it can, and your surroundings is going to lose heat to the system. So here, heat is absorbed by the system, and that's called endothermic. So if you try to heat up some water and you put your kettle on the stove and don't turn your stove on, your water's not going to boil. You need to add heat in order for that to happen. So your surroundings need to provide heat to your system. Okay. System, surroundings. In order to even talk about energy, we need to figure out the units and learn how to convert from one to the other. So the energy unit that we're going to use is the joule. A joule is 1 kilogram meter square per second square. This conversion is important because anytime that we calculate work is usually calculated in units of liters atmosphere, so we're always going to have to convert to joules. So that's a good one to know. And then we know that 1 kilocalorie, which is also known as 1 big C calorie, is 4.184 joules, and this is also equal to 1,000 little C calories. Those are like, the big C calories are like what's on your nutrition labels. Okay, so if you have, say, 200 calories in something, it's actually 200 kilocalories. And we can convert that to joules. Your R constant, for gases, in Gen Chem 1, you used 0.821. And for energy calculations, we're just going to use this one. I will give that to you on any quiz or test, but that's the one that you want to use for R. All right, so let's go over some conversion practice. I'm going to show you one, and then you can try the other two. All right, so the first one, we're going calorie, big C calorie to joules. And we want to remember that big C calorie is the same as saying kilocalorie. And we know that conversion because we had it on the slide before. Okay. All right, so I'm going to set it up like this. You always start with the one that you're given. We're given kcals or big C cals. Okay, you draw your multiplication sign and your division sign. Whatever unit is here, you need to have here. Okay, so my conversion, and in the unit that we want, will go on top. My conversion was 4184 joules is 1 kcal. So you're going to take 100 times 4184 divided by 1, and you're going to get basically 4.18 times 10 to the 5th joules. I just put it in scientific notation because it was a super big number. That's how you convert. So the big thing in any of our conversions with any unit that we do is just to remember that that unit needs to cancel out, And the way that we do that is by having it match whatever is up top. Okay? So I want you to pause, and I want you to try the other two using the unit conversions I have on the previous slide, and then you can come back and check your answers. Here's your solution. Check, make sure yours makes sense. Okay. Internal energy. So the sum of all the kinetic energy, which we talked about, is the motion, and the potential energy, which in our problems is going to be the composition, so your bonds and stuff, of a system, is the internal energy. It is a state function, which means that we don't care how it gets from A to B. We just need the difference between A and B. So, for example, altitude is a good analogy. So, like, let's say you have a mountain, and we know that from top to bottom it's 1,000 feet. Well, you can just take a direct route, or you can take the scenic route. I don't care. All we care about is that you've climbed 1,000 feet. Mastering covers this with a much better illustration, so I will leave it at that. But just know that internal energy and enthalpy are state functions. So all we care about is the final and the initial. I don't care about this stuff in the middle. That's kinetics, and we will do that, but not today. So here's your reactants. Here are your products. A plus B goes to C plus D. So all we care about is the difference here. I care about that energy difference. So if I'm doing final minus initial, you take 20 kilojoules minus 40 kilojoules, your answer is negative 20 kilojoules. That's my delta E, just final minus initial. Easy peasy. Is energy gained or released? Well, my products are lower in energy, which means that energy was released because it got rid of some of it. So the answer is released. And we talked about this before. If energy is released, it's going to be an exothermic reaction, like a bonfire. All right. Take a look at this one, pause, take a sec to answer, and then you can come back and check your answers. Okay, here are your answers. Make sure this makes sense to you. Okay, so we have some sign systems that we have in order to determine if Q and W and delta E are negative or positive, and it just depends on whether it's exothermic or not, what the system's doing. So when we're talking about heat is going to have a positive symbol. And this doesn't mean like more than zero. What it means is that we're gaining energy. So think of it like a bank account. Anytime money's coming in your bank account, that's a plus. Okay? So if a system is gaining energy, it's gaining heat, that's endothermic, and you're going to have a positive sign on Q. All right? If you're losing that heat, so if your bank account, if you're losing money, that's a negative. Okay? So Q is always going to have a plus sign or a negative sign depending on if we're endothermic or exothermic. Okay? Work also has a sign nomenclature. So work done on your system, where the system can just kind of sit on the couch and do nothing and have work done, that's a plus. That's positive. If the system has to do the work and has to put in the effort, that's a negative. System's lazy. System doesn't want to do anything. So that's a negative sign for W. And delta E goes the same way that you can think of it the same way as Q. If energy flows into the system, that's plus. If it flows out, like your bank account, that's minus. So what we need to do is take the word problem and figure out what the sign is, because this equation here is ridiculously easy to do. We just need to figure out what the sign is on Q and W from our word problems. For the first one, we know delta E is equal to Q plus W we just need to figure out what Q and W are. So Q, W. Let's look. So calculate delta E for a system undergoing an endothermic process in which this much heat flows and where this much work is done on the system. Okay, so Q is right here, that's my heat. So I'm gonna take my 15.6 kilojoules, I'm gonna put it right there. It's endothermic, which we remember is a positive sign. All right, because heat is being required, it's gaining that heat. W is 1.4 kilojoules of work. It's being done on the system, which the system likes because the system can just sit there. So again, positive. So in order to do this problem, we just take 15.6 kilojoules plus 1.4 kilojoules, and we get 17 kilojoules. If one of these was in joules and one of them was in kilojoules, we would need to convert to one or the other. But since they both have the same units, we're good, and we just add and we're done. All right. We have a potato cannon. So what happens is you burn fuel, it creates an explosion, which then shoots the potato out of a gun and produces heat. So I want you to pause, I want you to calculate delta E, and then come back and check your answer. All right, you guys, one more. Pause it and try this. Okay, sometimes we are not given what the amount of work is. But we know that work happens when you have a force, when a force is caused by a volume change against an external pressure. So basically, if you think about a piston, right, where you have, here's your piston, all right? So you have an external pressure that's pressing down, P external. Here's your volume. Now what happens is a force causes either the piston to go down or to go up, which is gonna change the volume that exists in here. That's your distance, okay? So the P external is your force, there's your distance. When you calculate work, you're usually gonna have units of liters per atmosphere, and the answer wants it in joules. So you just need to convert when you're done. That's the biggest thing I see with this is people forget to convert. So make sure you convert. Okay, let's try this one. So you have a volume change. So when we calculate delta V, we just need VF minus, oops, not delta, VI. So my V final is here and my V initial is there. So in order to get delta V, because what I want is work in joules, and I know work is equal to negative P delta V. So final minus initial, I'm going to say 1.85 liters minus 0.1 liters. My delta V is 1.75 liters. My pressure is 1 atmosphere. So I'm going to take my work and I'm going to plug in negative 1 atmosphere times 1.75 liters, and I get negative 1.75 liters atmospheres. But I need my work in joules, so I need to go ahead and I need to calculate that. So I'm going to take, sorry, this is kind of cramped, but I take negative 1.75 liters atmospheres and I multiply 101.3 joules because this is my conversion factor, 1 liter atmosphere. I cancel just like we did before. And my final answer is negative 177 joules. Okay, there it is. All right, I want you to pause and try number 8. There's the answer. Check, make sure it makes sense. Okay, last one. All right, so now we're given all this information. What we want is delta E, okay? Remember what delta E is Q plus W. Let's see what we get. So we get a balloon is being inflated by heating the air inside of it. So the volume of the balloon is going to change from this number to this number by the addition of this much heat. Assuming the balloon expands at a constant pressure of 1 atmosphere. So now we have Q, and it says we're adding heat. So there's my Q. I need to calculate W because I'm given a volume change and a pressure. So my volume change is going to be 0.5, right? Because we get 4.5 times 10 to the 6th minus 4 times 10 to the 6th. So we're going to take minus 1 atmosphere times So here we go. So we have, that's your work. So we need to convert it to joules before we can add it. All right? So I'm going to convert 101.3 joules, 1 liter atmosphere. So the number that I get for that is going to be, I'm going to bring it up, and it's big, and that's fine. So my work that I just calculated from here is negative, and I don't even have to worry about sign here because I got my sign from my calculation, so I don't have to like translate. Okay, so now we take 1.3 times 10 to the 8th joules and we're adding negative 5.1-ish times 10 to the 7th joules, and we get 7.94 times 10 to the 7 joules. So I want you to do 10, and then we are done with internal energy, and we're going to move on to calorimetry. So try this one and check your answer. All right, check your answer. Make sure it makes sense. Nice job.